Last time I discussed random walk in the context of the diffusion equation, and then tried to construct an analog in the quantum language and showed that there is a problem. The unitarity condition imposes other kind of a constraint which are not equivalent to picking the direction randomly. In particularly the conditional instruction, which is essentially that if the coin's value is this, you move in this particular direction. That immediately leads to entanglement. So the coin and the walk cannot be separated. They are entangled states. You have to find a description in the larger Hilbert space, which includes both these degrees of freedom. Okay, I will give examples of how it can be done, but first let me give a lot of background information which you may have studied in what to call first courses of physics in terms of what is a diffusion process and what is a wave dynamics and how are the equations connected to various physical consequences. So I will briefly give this physics description. The diffusion equation was essentially this time derivative proportional to the Laplacian. I have just written it for the one-dimensional case that easily generalizes, so I don't have to worry too much about it. But this equation has a power counting rule buried inside the dependence of time and position, which one can easily see if there is a change of variable in various coordinates. Essentially, it's a Fourier transform which is often used, where the phase is e raised to I kx minus omega t. So this is standard phase of Fourier transforming both in position and in momentum. And if you plug this thing in, the derivatives basically become powers of position and the wave vector k and the frequency omega, and the dependence turns into a dispersion relation where omega is proportional to k square. Okay. Omega comes from here, k comes from that side, and this is a standard dispersion relation for describing classical diffusion. In the quantum language, you will write its energy proportional to momentum square by saying that energy is h cross omega and momentum is h cross k, etc. But that is fine. This simple quadratic connection comes out. Now, consider the equivalent description for waves. So wave equation, I'll use the same variables, but it's understood. Looks like this. Can derive it or understand it in many different ways. For example, the simplest setting is what happens when you have a string tied at the two ends and you pluck it like a musical instrument. It oscillates, and what is the equation? It comes out like this. And c is basically the speed of the wave, how fast the phase velocity of the corresponding mode is given, and the unit of c is a speed basically because it's the time here and there is a space here. If I again do the same Fourier transform over here, it gives a dispersion relation where omega is proportional to k. Okay. Because there are two powers and the proportionality constant is actually c, so it can be more explicit here. And this is the different relation compared to that. There is a interpretation in terms of frequency and wave vector here, or if you go back to the time and space coordinates over here. So, for example, this is equivalent to the distance, which is, well, actually these are expectation values. So, diffusion equation, the relation behaves like this: how fast you can move goes to the square root of t. Well, it's not even x, it's actually x square. Probably better than. The mean distance of diffusion is basically behaving like a square root of time of evolution. If you try the same thing over here, it is proportional to t square. So just the wave front is moving and it's a constant velocity, you go that far. So the propagation speed is different in the two situations. And if you now think about it, what is the physical process in which such dispersion relations appear? So there are many examples. But the key property here is that this looks non-relativistic and this is relativistic for the particles. Energy proportional to square of the momentum, and here is energy is proportional to momentum. It doesn't have to be speed of light, whatever the speed of the wave is, the proportionality constant. And this will get buried in any description when you try to construct the quantum generalization. Okay, the wave equation is going to look different than the diffusion equation when you try to calculate the properties of how the area or the distance which is covered starting from some initial point. There are lots of examples other than the simple things which I already mentioned, like this being a Brownian motion and this being a wave propagating on a string, because these equations don't necessarily remain in this mechanical setting. They can be applied to many other situations, and one, it's going too far, but anyway, one thing I can point out is that you can get this kind of dispersion relations even in crystalline systems where the waves will have different behavior. Instead of having a mechanical wave or electromagnetic wave. You can also have phonons, vibrations, all kind of rotational couplings. Everywhere there is a simple harmonic motion. It's very common in many situations. And one example where both these things are seen is that of a magnet. So in a magnet, you have a situation where all the spins are lined up. They're all fixed because of, well, some couplings or interactions or whatever is buried inside here. And then you can ask if there is a low energy state where everything is parallel. Suppose I perturbed any one of them, they will vibrate because the lowest energy state is the one where everything is parallel. And what happens to those vibrations? So the vibrations in case of magnet, they are called magnons. Just like photons is for light, there is some vibration. You can write a quantum variable for it and call it a magnon. So in case of magnons, if I have a ferromagnet, which is the common material in compass or what you call a piece of iron, something like that, where all the spins are actually parallel. So the ferromagnet, this dispersion relation, where the omega is proportional to k square. It's a wave, but it's a certain property which you can describe by saying how quickly this oscillation of the magnetized spin come back to its original place. And instead of this, if I have an antiferromagnet where neighboring spins are opposite, those materials also exist, and you work out again the perturbation analysis for it about the equilibrium, you end up with a dispersion relation like this. So there are many physical situations where you see all these kind of effects, and the applications depend on the actual material you are dealing with. I will not go into too much detail, but I wanted to give you just some physics background that these kind of features are common and you have to deal with the situation appropriately. You have to find the proper variables. Okay. So now I go back to the quantum walk. This dynamics is in the Hilbert space, which is tensor product of the space coordinate wherever it goes on the graph and the coin coordinate whatever it does. They are untangled. You cannot talk about only one or the other, otherwise the unit tragedy gets into trouble. Now, the question is how large a coin space you can use, because the coin has its own dynamics. You have to toss it, and you have to figure out what is the operation corresponding to the toss of a coin, not just a movement on a graph or a lattice or something like that. So, if you are going to say that I'm going to toss a coin and every toss I will toss a different coin, the coin space will become as many number of steps as you take in the walk. That is too much. And so it will be nice if I can deal with a coin which has a finite amount of space. And people tried various things and they figured out a specific situation where the space can keep on growing on the graph, but the coin stuff remains finite. Like a head or tail, there will be some generalization of it, but it's a finite dimensional space and you can take as many steps as you want on the walk. Okay. So, best thing is actually to define it on a specific example, and I will consider for simplicity the situation for what I call regular graphs. Okay. The definition of regular graph is that each vertex has same number of neighbors. Okay, this is a common situation in a crystal. You have some point, the same number of neighbors, there is a translation invariance essentially. So no matter where you go, you have the same geometry, and this number of neighbors is called degree of the graph, and I will denote it by D. Okay. Then it turns out that I can choose the coin to be of dimension D. I don't need too many of them. As long as at every point I can decide various directions, those are the directions that will get associated with the coin, that I move this way, that way, etc. And it is enough to have coin of this particular dimension. So now I have to give a explicit construction, and one of the example is called flip-flop walk, which is defined in this H of graph, whatever this vertex is. Cross H of D. Yeah.
The dimensionality of the coin
is
equal to D or 2?
D.
So the coin, I mean, here the coin is not exactly the coin. When we toss coin, we have D possible to coin.
Yeah. Because at every vertex you have to decide there are D neighbors, where do I want to go to? Okay, you need those many possibilities in the coin. Otherwise, I can't. If it is one dimensional, yes, it will be 2, but higher dimensional, you need more. So what it does is it has 2 operations. So so the walk is equal to the coin toss times shift. This is a generic sequence which you will need for any walk. Where is the other way around, but it doesn't matter. They alternate. You toss a coin and then you shift accordingly, toss a coin again and shift accordingly, etc., etc. So let me follow some simple notation, not to confuse the points. Okay, that is good enough. So the shift operation, so this is this particular example. What it does is you have some amplitude at some position and some direction. So this is well, both of them are vectors, but it's fine. X is the position on the graph, and L are all the unit vectors which go from a point to all its possible neighbors. That is this Hilbert space. And what it does is it moves in this direction, but then it reverses the state of the coin. That is why it is called flip-flop. And there are very trivial properties associated with this. One of them is you can always define it on any graph, because once a link is given, you can go from x to x plus L by taking this unit vector, or if you start here, it will go back to x. And so this has a simple structure that if I repeat it, it's identity. It's a reflection operation.
Here, L cap is not the result of coin toss. Here, L cap is not the result of coin toss.
This is a shift operator which is conditioned on the coin toss. So there is a state of the coin, and depending on the state of the coin, you shift in that particular direction.
So are those two the same? So the thing, the L cap, so once we are doing the coin toss, we are getting some result. So is that result same equal to this L cap? Or like it is?
Yeah, this is a result of the shift operation conditioned on the coin toss. So it's a walk. You toss a coin, you move. You toss a coin or move. How do you move? Depends on the condition of the coin. Okay.
When you have x plus some alpha times based on x plus alpha times.
There are many directions. The directions are covered by the degree. Yeah.
L cap is representing only direction.
Yeah, it's a.
So to reach to the other point, it is not just L cap. It should be some way one can put alpha or some.
No, it's a unit vector which goes from one vertex to its neighbors. That unit vector is constant. If it's a crystal, you define whatever it is. It's a unit vector in that particular direction. It's a translation invariant system. The unit vector will be the same no matter where you are on the lattice.
Isotropy. Isotropy comes in.
Not isotropic. Regular. Isotropic implies a rotational invariance. Crystals don't have that. But they can have a regular property where no matter which location you are, you have a fixed number of directions.
So when you like to write S square equation, why do you write S square equation?
Because you
They are not.
now apply the shift operation again. By the same rule, you will go back to AX and this will become plus L.
They are not the same shift operators. They are not the same shift operators. One of them is the inverse operator.
No, if you write it as an operator, what does it do? So take the site and adds this particular vector to it. Okay, that operator is a reflection operator. What if I apply to this particular state, the operator? Take this, add it over here and flip the sign of this, which will come back to this state. See, there are two things. One of them is I wrote the amplitude, but when you are dealing with quantum theory, you will find that there is a transformation of the amplitude which will express as a matrix. And the matrix doesn't refer to where it is acting, okay? It is a general description anywhere it can act. And the matrix will have this property.
Also, E is the amplitude of how much we shift.
No. This is the amplitude of being at that particular location. The total state of the system will be a distribution over all the lattice sites. And this is the component at that particular lattice site. How it will transform. And then a second operation which needed is a coin toss. What should it do? And the flip-flop uses actually the version which is the same operator that was used in Grover's search. So what does it do? Well, in the Grover search notation, it was written as the projection operator onto the uniform state minus the identity, which is considered the evolution operator. It's a reflection operator again, but that was a notation. Here, if I want to apply it, what it does, it doesn't change the value of x. That is because it's going to act on only this particular state, but it will mix the various components along various directions in some particular way. And the copying this notation, but now writing it little differently, that x L prime it looks like this. That what this does is creates the average of all the amplitudes at that particular location, which is x and L prime summed over all the L prime. 1 over d is because this is an average. I have to, how many values of L prime are there? There are d of them. And this 2 is the same factor over here. And this identity is nothing but the amplitude, whatever it is. Okay. Again, if I look at it, because I know this is a operator, which is again a reflection operator, if we'll have the property that if I perform it twice, we'll get back the identity. The first time I do this, apply it again, you will get back to this stage. And the total process, which is this, is defined as alternate applications of these two operators. This is means for the purpose of definitions, and people worked out all kind of details to show that it actually does reproduce the quantum walk, which is conditioned on the coin but also unitary. Okay. That is guaranteed because you have chosen the operators in some particular manner. The more elaborate point is to actually show that this reproduces the wave behavior. And for that I have to do a detailed illustration about what these definitions actually do in a particular simplistic scenario. So the simplistic scenario which I'm going to choose is just a walk on a line, d equal to 2. It's easy to analyze what happens in this particular situation. All these general definitions will simplify. So you have to choose a basis. So let me take this x-axis. Some convention I have to pick, and that is fine. So I will use the conventional notation for the eigenstates, which are eigenstate of the sigma x, the Pauli operator called plus and minus, and the projections are 1 plus minus sigma 1 by 2. This projection operator. I need some label, and this L has only 2 choices. So I denote this choice by this direction, and if I want to look at only one particular component, I can use the projection and look at only that component. So now let us write it down, the simplified version of this transformation. And now let me just write down the, eigenbasis is this, and the transition operator is sigma 3 between the eigenstates. This is, well, all connected to a particular notation I choose here. If I had called this one z-axis, then this will become the state 0 and 1. This will become 1 plus or minus sigma 3 by 2. And the transition operator will become sigma 1 instead of sigma 3. But they are all interrelated, it's just for the sake of notation. So if I apply sigma 3 on this state, it will become minus, and if I apply sigma 3 on this state, it becomes plus. Okay. So now I am ready to write down what this transformation is. Okay. So A, or rather I will just write the operator as. What it does, it takes from the point x to the new point, which will be dictated by whether the direction is plus or minus. So I have to write a general amplitude, and looks a little bit complicated, but let me write the expression. It's going to act on all the points. But one part will have this action. It takes x to x plus 1. And there will be other part which will have the action which is takes x to x minus 1. When will this occur? Well, if the vector here is plus. Okay. So that will something I can obtain by writing 1 plus sigma 1 by 2, and correspondingly 1 minus 1 sigma 1 by 2. So what it does is takes whatever the amplitude is, finds out how much of it is in the plus direction, and moves that one step forward. Here it takes the amplitude, finds out how much is in the minus direction, and moved it in the backward direction. But this is not all, because I have to put this flip-flop sign inside it, and okay, I didn't leave enough space, but let me put it over there. It's going to act afterwards. So the actual transformation looks like this. Finds the operator. This part is the movement in the x, and this is the change in the state of the coin, where instead of being L, it will become minus L. The order of this don't matter. This is in one Hilbert space and this is in another Hilbert space, but the tensor sign I have not bothered to write down explicitly. So this is the effect of this operator S. This way, this is a matrix because of the summation over x, all the coordinates.
One second. Which operator belongs to which Hilbert space? There are three operators. There are three operators.
As I said, it is in the tensor product space. I have not bothered to write the symbol, but if I want, I can add this little sign in between here. Yes, there are various factors, but some part acts on the position space, some part acts on the coin space.
So for being a particular state, let's say, it shifts the entire state's amplitudes to either its neighbors.
Yeah. So every point will have many different components, and different components will move in different directions. So the total distribution is going to be in this large Hilbert space. What about the operator G? Well, that becomes kind of much easier to construct because D is equal to 2. So this normalization is 1. This is a sum over all the components, and From that you are subtracting one of the components, and since there are only two components, is the other component which is remaining. So what G does is takes this AXL and shifts it to the other component. And what is that operation is this transition operator. It's only sigma 3. So this is just interchanges. I'll have to write sigma 3 first. That's all it does. And so then this operator W, the sigma 3 kind of disappears. It just becomes this. And yeah, this may look complicated. This one is actually simpler to understand and interpret. What it is doing is at every point looking at the plus and minus components, and the plus components keeps on moving in one direction, minus component just keeps on moving in the other direction.
Is that get x plus 1 right?
Yeah. And these are just the two wave fronts. You started here, constant speed. If the velocity is positive, you go all the way. Velocity is negative, you go on the other direction. And this is a remarkable feature which goes all the way back in here, which I forgot to mention earlier, but I can say it. So if you want to say construct say this W acting with some t number of times, the expression is rather trivial. From this, it is just x plus t. Just decompose the two things and propagated them independently. And this happens to be the generic solution of the wave equation. So I can now go back and write it down. The most general solution of this equation can actually be written down explicitly. Not so easy for that particular case, but this is related to the rather simple identity that I can rewrite this equation trivial factorization after shifting this operator onto the other side. And all these partial derivatives, they commute. So whether I write this one first or this one first, doesn't matter. C is a constant. So what is the most general solution? And D'Alembert wrote it down that phi is equal to just the solution of those two factors. this phi plus and phi minus are two parts which are completely unspecified. They can be any arbitrary functions. But the argument is such that for any arbitrary function, if I apply this operator, in one case this will become 0, the other case that will become 0. And what we have reproduced here is essentially this particular feature. You break it down into two parts. One behaves as a component which is going to move in the positive direction. Distribution of amplitude doesn't matter. What matters is the relation between space and time. So this basically two components move independently. And this behavior we have reproduced by construction of this flip-flop walk. We had to introduce some coin doing funny things, but ultimately what that coin is doing is some kind of projection. And you find this behavior coming out. And so it is a unitary process, and it is a wave process, and it shifts the amplitudes in appropriate manner. And so you can call it a walk, whatever. You start at, say, initial point x equal to 0, it's going to spread out. And this is just a one-dimensional example, but you can do a lot more work and prove that, yes, in the d-dimensional, this situation works. And you can take a d-dimensional lattice. You can, if it is a what you call hypercubic lattice, all the components will act independently and this thing will follow through in a very trivial fashion. But it doesn't have to be a hypercubic lattice. You can have, say, the simplest non-trivial one is a d equal to 3, which is a lattice of a graphene system where all the hexagonal structures are there, but every vertex has 3 neighbors. And you can implement it in that geometry, and that also does the same job. You will find that there will be propagating modes which move with some constant speed. And if you're, well, I don't know, anybody has done enough of solid state physics, they will know a little bit that graphene's peculiarity arises from a dispersion relation which is relativistic.
In our wave equation, there is a notion of speed, but what is the notion of speed in the operator?
In here, it's just equal to 1 in the normalization I have chosen. In one time step, I go from x to x plus 1. So the speed is 1. So one can now make more detailed structures. I'm not going to go into higher dimension, but at least point out what more can be done in a one-dimensional situation as well. And that is to modify the system a little bit, saying that I have 3 options at every point. Either I move to right or left, but with some amplitude or some probability I remain where I am. No movement. And it has an interpretation going back into this equation for the wave equation, which is in a relativistic scenario known as a Klein-Gordon equation. And it's a little bit of excursion into particle physics, but the equation is rather trivial, that what you introduce is not just this time derivatives, but the next term, which is essentially the field itself. By this rule that right hand side is not 0, but I put m square over there. And why this appears in particle physics, that this is actually the relativistic version of this particular dispersion relation. These are massless modes. You gave it some mass. If you give the mass to be too large, you will go back to non-relativistic situation, but don't have to go that far. You can have m which is kind of comparable to the magnitudes of E and P. And what does it do? Well, you can do the same trick of factorizing this thing, and that gives us some idea. And it is a kind of convenient after this factorization to break this up into 2 coupled equations instead of one which has a second derivative, something which has a first derivative, and that can be written as this will have 5 plus, okay. So it's very easy to check that they are equivalent. All I have to do is I take this operator and apply it on this particular part. The left hand side will be just exactly become that, and the right hand side I will get derivative of this, which is equal to im phi. Im gets squared to give minus m square, and then the equation will be completely in terms of phi plus. So with the notation is phi is equal to phi plus. It can be broken up into two components, and this now has a interpretation that one component is moving forward or backward depending on phi 1 minus, but there is some little probability that it will not move. There is no derivative operator on the right side, so it will remain in the same location. And we can easily now incorporate this structure into this equation, and you will see that the mass is kind of component which doesn't move. Okay. These other two factors corresponds to momentum. Some momentum component goes in one direction, some in the other direction. But if there is an action by mass, the coordinates are not going to change, it's going to remain in the same place. So that formula can be written down now in a particular signatures where I have to give some probability or equivalently the value for the mass. So whatever I was writing somewhere over here, but I have to this whole expression, whatever it was, x sigma 3 1 minus so I made a discrete version where the operator shift part now is changed a little bit. This is the component which moves, and I gave it some probability p. But with probability 1 minus p, there is a component which doesn't move. And this doesn't change. It acts only on the coin. It has nothing to do with movement at all. So now I can write this W, which will again root 1 minus P So this is the same thing which was there earlier, the two components moving independently in opposite direction. But what is the action of this particular operator? It is sitting at the same location, but you are acting by sigma 3. And that is equivalent to this situation where action of sigma 3 is just changing phi plus to phi minus. And vice versa. So this so this is a discrete analog, and it moves at speed less than 1. Well, according to this dispersion relation, depending on how much amplitude you put inside here, you can find the velocity of this. It's not, well, square root of p square plus m square in some sense divided by how do we define in the relativistic thing? The velocity is just p divided by e. That is fine. It's a fully relativistic. Magnitude of p and e are equal. Non-relativistic or slower particle, magnitude of p is less than the magnitude of e. So you can construct this kind of a walk also, where some amplitude will remain at the original location and it will spread, but it will spread a little bit slower. So this is one particular structure, and which has been explored in lots of different geometries. As I said, they are all regular graphs, but you can construct many different kind of regular graphs, and I will give some examples. Yeah.
So in this case, even if the system does not move, but the states flip.
Yeah. You need a relation like that. Whenever you make stationary, this phi plus and phi minus have to change. So examples are whatever, hypercubes, graphene. It has even been tried out for fractals, which are not dense lattices, lots of empty spaces, but you can still describe lot of fractals by regular graphs, and the whole all this construction goes through. And yeah, that's probably as much as I can discuss. And I mean, there is a certain amount you can study it analytically, but if you want to study more generally, you can do a numerical simulation. It's not complicated because these rules are very straightforward. Just have to construct a particular graph. The numerical part will have the constraint that the graph will be finite. Okay, you can't really deal with infinite stuff, but you can take a large enough lattice and see how these various things are going to interplay with each other. Yeah.
Somehow X of projection operators as identity.
It's a tensor product. It's, you have to look at it in the whole space. It acts at every point, and yes, you sum it over, it becomes identity, but it's the other part will have a distribution. The coin component will manage distribution. So for every particular component, yes, if you sum over X, it's an identity operator. So this is one particular example which has been studied in detail because it's quite simple to construct and quite flexible to deal with various kind of geometries also. There is another example which I want to point out, which has been also studied. These are all discrete structures, but there is nothing unique about it. That is a usual connection that this continuum description is defined in a more restricted fashion. Many discrete description, when you take the limit of some spacing going to 0, they might be individually different looking, but they go to the same limit. That is the advantage of the continuum description. On the other hand, the discrete formulation sometimes is more powerful. One reason which I mentioned in the last lecture, that it allows you to get rid of noise, which is not possible in the continuous description. But the other part which is relevant here is that you don't have to make specific assumption about continuity, about limit existing, things like that, where you can construct derivatives. It can be just finite differences, and that allows possibilities which are probably not described in terms of derivatives. So examples of those types also exist, and in particular there are many applications in study of the quantum information theory, where the discrete description is actually more powerful than the continuum equations. One example which I had pointed out in the previous course was something known as a Krauss decomposition for the evolution of a quantum system, which is more powerful than Schrodinger's equation. So I will describe another scheme, a different discrete scheme. If you take the limit, it is going to go back to the same properties, but it is also interesting in its own right. So I'm going to erase this in case you want to take a picture. And it is connected in some sense to this idea of decoupling the two modes, one moving one way and another moving other way, but in a different scenario. So let me just define it explicitly for the one-dimensional case, which is this example of d equal to 2, but it is more generally constructed in a language which alternates between these positive steps and negative steps, and it is called staggered walk. And this is something which is very well known. In the description of lattice field theory. I will not go into the detail, rather I will give the description, which is very straightforward. So again, yeah. I will write down the situation about what we want. This Laplacian operator on a line basically, it's a quantum case, so let me call it as a Hamiltonian. It is proportional to a matrix which can be written as nearest neighbor differences. So it has the structure of this particular type, and that is a very generic property that the Laplacian is proportional to average with convention I'm taking is -1 for the neighbors, and I have to put the sign properly, or doesn't matter. It's a proportionality sign anyway. This is an operator which is heavily used in lots of numerical methods. If you want to define a discrete Laplacian, which is part of lot of partial differential equation, the simplest definition is you sum over all the neighbors and just subtract the local value. And whatever comes out is equivalent to the Laplacian. And this actually is a very powerful numerical method to solve Laplace's equation in lots of different geometries and lots of physical situations, whether it is electrodynamics, where you have to solve Laplace's equation, whether it is some finite element analysis, you have to solve for material properties, etc. How do you construct Laplacian? You do that, and if you iterate these steps many times, every point you go, you just replace it by the average of the neighbors, it converges very well. Because numerically also it has nice properties, and you just keep on doing this till you converge, and whatever the distribution you get at the end is a solution to the Laplace equation. So anyway, the structure in one dimension just looks like this, where I have changed the normalization a little bit, but essentially you are taking the local value which is opposite to the sum of all the neighbors. and in one dimension there are only two neighbors. Okay. So it can be now broken. So I'm going to write it as a sum of two different components, where I'll just write it, one of them, well, doesn't matter, E and O stands for even and odd in this particular case. So one is going to be on the diagonal, which will be there on all the three lines which I put over there. And the other two lines are going to appear like this, and HO has to recover the remaining stuff, which again three diagonals will have 1, 1 and 1, but then the missing part is on this side. And it looks like this. So if you add the three things, this is -1, this 1 and 1 is 2, and this other -1 is here, and the same way it follows here, -1, 2, -1, etc. The reason for doing this is twofold. One of them is this HE and HO are block diagonal. They are all made up of 2 by 2 matrices. And the other property is that they have first derivative structure. Because if I, just like I interpreted this as a Laplacian, if I have 1 and -1 and nothing else on that line, what it is doing is a nearest neighbor difference. But now what has happened is I have separated the two first derivatives in different ways. Here it was -1, 2 and -1. So this is the derivative on one side. The other derivative on the other side is sitting in this matrix. The same way, this is forward derivative in this matrix, there will be a backward derivative in that matrix. It has kind of shifted, but the two derivatives have ended up in different matrices. Remember that in the same matrix, this is a forward derivative in the direction, then this will be a backward derivative. But what has changed is half the forward derivatives are one side, half the forward derivatives on the other side, and that is done keeping this block diagonal structure under construction. So the two advantages. So what is the advantage of a block diagonal structure? So these 2 by 2 blocks you can exponentiate it very easily. whichever way you want. The common thing which you have seen is you can write this as a combination of polymatrices, and you know how to exponentiate the polymatrix. This is a Hamiltonian, which is Hermitian. That is definitely true. So even when I have made this block, the hermiticity is not destroyed. Okay, this off diagonal here and here, they are there. So these are so Hermitian. That I have not given up. Laplacian was a Hermitian operator, and this thing is also Hermitian. Even though I have split it up into different components, but they can be exponentiated without any problem. Not too much algebra is involved, only 2 by 2 matrices. So where is the quantum theory buried inside here, that this He and HO do not commute. So block diagonal structure make it actually translationally invariant. The same block is going to act at all the places. The non-trivial propagation which has to go outside the block, because if I just take one of them, no matter what time I took, it is going to remain within the block, the exact exponentiation. So I have to propagate. The propagation comes because of the fact that these two don't commute. Okay. And then the evolution is defined. So one more thing which is there, that in this I'm stating without proof. No matter what the dimensionality is, here it is only for one dimension, but in any dimension you can find this decomposition which involves only two components, nothing more than that. So what is the definition of a walk? So I just have to take a definition where there is a unitary operator for evolution according to the even part, and another unitary operator for evolution of the odd part. And that's all that is needed. These two factors are not going to commute. So if I take some power like this, they will keep on alternating. And then you can see what will happen directly or indirectly. Some of it goes back, some of this goes forward, and it can be, worked out as a exercise. Requires more work, that does it come out like this wave equation at the end or no for this particular evolution. But the point is that this is again unitary by construction, and so it is not equal to the exponential of a Laplacian. That comes because these two don't commute. If they commute, then exponential of the sum is the product of the individual exponential, and then this will be exactly the exponential of Laplacian, but these two don't commute, and you will produce a non-trivial behavior of that, which is different than exponential of Laplacian, and that is what converts it from this diffusion operator or the Laplacian operator to a relativistic walk. Okay, so there are things like Trotter formula which relates the subleading terms, etc. One doesn't have to go into all that particular detail. From the construction point of view, you can do this, and now you can actually construct, take this operator and write down just the product of these two and see what happens. So you'll find that it will have extra terms, not just the nearest neighbor, but something extra will appear. And that extra term is enough to give all the relativistic property. So what happened here? You have done this decomposition into two modes in a different way. But in the last class, I said that you could not write a unitary operator which is local, okay, of this particular type. Hamiltonian was local, but when I tried writing a unitary operator with some A, B, C, etc., the two of the components basically just became zero. So here you have, so this W is local, because it's not going to go arbitrary far away. But it is the translation invariance will come only in steps of 2, not in steps of 1. That is because of this structure. This block will go into the next block, but that requires you shift by 2 units. So when I did the exercise in the last lecture, that unitary matrix with some A, B, C, I wrote A, B, C on the same lines for every step. Here, that symmetry is broken. Alternative lines of that operator are going to be different. And that is enough to bypass the constraint of this locality and unitarity being simultaneously present. You have given up a different assumption. And this now can be analyzed if you want. You can construct this explicitly. It's a local operator. You will find different versions, and even the exponential can be made easy. So these blocks are what is here is I minus sigma 1, and is exponential of a polymetric, so you will get some cosine terms plus some sine term times sigma 1. Okay, depending on what is the value of time, you will get cosine of some time and sine of some time, and that will be a matrix which will go inside here, and then you keep on multiplying it. The life can be simplified, so I will leave it as an exercise. We are all working with polymetrices and you just change the basis. You can redefine everything, replace sigma 1 by sigma 2. The point is that then this stuff will become real. And then you can multiply this thing and see what every walk step does. And well, that is simple enough to figure out that yes, it will reproduce the same Klein-Gordon equation in a certain sense. So, yeah, I will leave that as a exercise. Just work out this particular product and see what you get as an evolution step. And it has all the properties needed for the wave equation, together with all the locality and unitarity explicitly satisfied. Okay, I will stop here.